In our previous discussion, we learned the basic spatial themes, which are the basis for spatial analysis, the core of spatial analysis. In this discussion, we look into different spatial analysis methods along with possible examples. To begin with, I may say that spatial analysis comprises analysis and synthesis of spatial data, implying the professional interpretation of the results. Spatial analysis, in many ways, is the crux of spatial information science because it includes all the transformations, manipulations, and methods that can be applied to spatial data to add value to them, to support decisions, and to reveal patterns and anomalies that are not easily recognized. In other words, spatial analysis is the process by which we turn the raw data into useful information. The spatial information science share information about the realities of Earth's surface, while the spatial analysis adds further informative content and value to them. This can be done by adding attribute information to the spatial information. Before the popularization of GIS, which is so popular in modern day, or spatial information science to which we are referring to, geographers were carrying out spatial analysis, but with traditional methods, manually. The modern day GIS or SIS are improved methods of spatial analysis, which has its root in analytical cartography. Here we look first at some definitions and basic concepts of spatial analysis. The basic idea of spatial analysis is essentially location-based information. This means locations is essential, that analysis carries out without knowledge of location is not spatial analysis. So spatial analysis is a set of methods whose results change when the location of the objects being analyzed are also changed. For example, calculation of an average income for a group of people is not spatial analysis because it is not dependent on the locations of the people. But if supported with space identity, for example, randomly if I take Lajpat Nagar, Lane 3, New Delhi, population, this becomes spatial because the results depend on information about where the sample is located. This makes spatial information science an ideal platform for spatial analysis because its data structures accommodate the storage of object locations. The spatial relationships types. Some very commonly but very important spatial relationship types can be known as, for example, adjacency, contiguity, overlap, and proximity. These are four ways of describing the relationship between two or more entities. Adjacency is when two polygon entities are directly connected to each other, sharing a boundary. That would be known as the adjacency. The contiguity is the relationship between two or more entities when they share an edge, while an overlap occurs when a single entity shares the same location or partial location of another entity, while proximity is defined as being close enough that you can establish contact with each other without having physical direct contact with each other. But all of these spatial relationships are important and very relevant in spatial information science. There are several methods for testing spatial relations between geometric objects. Each takes as input to two geometries and evaluates whether the relation is true or not. If you take the example of equals, where the geometries are the same then we will call it as equals in spatial information. Another can be disjoint, where the geometries share a common point. The intersects, where the geometries intersect each other. Similarly, touches, when the geometries intersect at their boundaries while they are touching each other boundaries. Crosses, where the geometries overlap each other. Another can be within, when the geometries within each other, one another. Contains, when one geometry completely contains another geometry. There can be overlaps, where the geometries overlap each other. Or relate, when the intersections between the interior boundary or exterior of the geometries. So these are some spatial relations and analysis on geometric objects that is very relevant for spatial information, representation of ground realities and spatial entities. Another can be the topological relationships. The topological relationship exists when two objects are connected to one another. But one object has a specific set of rules that dictate their relationship. When we create topological relationships, it ensures that related features are free of error. Now, some of the examples are the dangles. When the end vertex of a line does not snap to a point, line or polygon, resulting in a dangle. Another could be overshoots. Overshoot occur when a line endpoint does not snap to another feature, resulting in a line extended too far over the another entity, spatial entity. Another could be undershoots, the just opposite to the overshoots. Undershoots occur when a line's endpoint does not snap to another feature, resulting in a line a little short. The slivers are often the result of imprecise digitization in spatial information science, which create undesired gap in polygons. So these gaps would be the sliver polygons. The overlaps, they are unwanted extended polygons or lines that cover each other. Although data can't always be free of error, we can set topological relationships to improve the data quality. These are all unwanted errors that require data cleanup. But each one has spatial relationship associated with them, and that is why we are calling it as topological relationships. Now, some examples of topological relationships for spatial objects. Now, spatial relationships refer to the way objects are arranged in relation to one another in geographic space that we have discussed earlier also. These are some examples of topological relations for spatial objects with respect to point, point line and point area entity. The upper example is for point, point line and point area entities, where the point can be within the point entity or near to the point entity. The point line would be on the line, point is on the line or near to the line. And point area example could be point within the area or on the area. So these are topological relationships. Where lower row examples are line with respect to area and area with respect to area. Here the line to line topology relation could be while the two lines are intersecting each other. Another, instead of intersecting, it is crossing. So it won't be creating the vertex. And another can be the flow into the another line. One line is flowing into another line. The example of line and area entity would be if the line is intersecting the area or it is just bordering the area, touching the area. Similarly, area to area relation could be overlapping inside another area, one area is inside another area, or adjacent. The two areas are adjacent to each other. So in these examples, very clearly topology or arrangement of locational entity possibilities are depicted. Some examples of methods for testing spatial relations between geometric objects, where the example is for contains and touches. Here each takes as input two geometries and evaluates whether the relation is true or not. The diagram shows contains when one geometry completely contains another with point, line and area entity, with several spatial combinations and possibilities. You can see here. Another example is for touches, when the geometries intersect at their boundaries with base geometries of point, line and area entities. So you can have many options. There can be no containment relation possible or no containment relationship possible or not possible. So that way I would say that these are possible relation between two geographic databases. Some more spatial relations and analysis on geometric objects. For example, distance, buffer, convex hull, intersection, union, a geometry that contains all the points in both input geometries, differences. These are all good examples of how we can see spatial analysis on geometries. The example of spatial analysis methods on geometries can be the buffer. The buffer is a geometry that represents all the points whose distance from geometry is equal to a user-defined distance. On the contrary, convex hull, a geometry representing the smallest polygon that can enclose another geometry without any concave area. You see the example here and how different geometries are being produced with the kind of relationship. The intersection, a geometry that contains just the point common to both input geometries. While differences, a geometry containing the points that are different between the two geometries. Distance, the shortest distance between any 2 points in two geometries. While union would be a geometry that contains all the points in both input geometries. So I am just giving you an idea as to what are the possible spatial analysis methods while taking different geometries. Now these are all spatial entities, and this way we are presenting in spatial information science the different kind of data. Another can be queries and reasoning. We have seen this example earlier also, but I am taking it in this connection. I am taking the queries and reasoning as the basic analysis operation. No change occur in database here and no new data is produced. But these are the basic of analysis operations in which the spatial information science is used to answer simple questions posed by the user. As I am saying that no change will occur in the database, but no new data will come up. The operation vary from simple and well-defined queries like how many houses are found in 1 kilometer of this particular point on the left side of the example, to a very vague question like which is the closest city to New Delhi going eastward, where the response may depend on the system's ability to understand what the user means by going east and what we mean with closeness. Here the scale would come into the picture. Another could be measurements. Measurements are simple numerical values that describe aspects of spatial data. They include measurement of simple properties of objects like length, area or shape, and of the relationships between pairs of objects like distance or direction. Another could be transformations. They are simple methods of spatial analysis that change the data sets, combining them or comparing them to obtain a new data sets. And eventually, we can draw some new insight into the changed information which is being depicted in the spatial information. The example is of delineation and classification, which is being represented here. Here the example of reclassification, where the modification in attribute values are made to produce new object datasets. Another example of cookie cutting, where overlaying a dataset is made using one dataset as sieve or cookie cutter to select a subset of other datasets. You just look into the images which have been presented before you, and you would understand that how reclassification produce a new object datasets, or how cookie setting, where overlaying of dataset using one dataset and sieve or cookie cutter select another subset to produce another data out of it. So these are another important way of reclassification. Now here some more spatial analysis of distinct categories, where we are looking into transformations, descriptive summaries, optimization, and also hypothesis testing, etc. All in all, I would say that these are some very important and interesting characteristic of spatial information science which we have dealt today.